In this video, I will show you how to use your basic integration techniques to solve problems involving position, velocity, and acceleration. I will also show you how to find the general and particular solution to a very basic differential equation. And finally, I will demonstrate how to show that one function is the antiderivative of another. A particle moves along the y-axis with acceleration at time t greater than or equal to 1 given by this function. At t equals 0, the particle is at rest, and its position is y equals 4. Find an equation for the particle's velocity v at time t. T is greater than or equal to 0. So let me say a couple of things. In the past, we have often spoken about the relationship between f prime, and f double prime. The original function, the first derivative, and the second derivative. Well, now we will talk about the relationship between y prime, and y double prime. I'm using y because the particle is moving along the y-axis. So y will represent the position of the particle on the y-axis. Okay, so y, I'm rewriting it for another row here because I'm going to change the y prime and the y double prime. But y is the position. Y prime is the velocity. And y double prime is the acceleration. So everything we know about f prime, and f double prime will now apply to y velocity, well, I should just say position, velocity, and acceleration. Notice that if you take the derivative of a position function, you get the velocity function. But you can do this the other way around. If you take the integral of the velocity function, you get the position function. Similarly, if you take the derivative of a velocity function, you get an acceleration function. Going backwards, if you take the integral of an acceleration function, you will get a velocity function. And that's what we need to do right now. In order to find an equation for the particle's velocity, we need to take the integral of this acceleration function, and that should give us the velocity function. So the velocity function will be the integral of the acceleration function, and the acceleration function is 15 t to the 1/2 power minus 8t. So let's take the integral of this in order to reveal the velocity function. Of course, we will do the power rule of integration. So here's the 15, which I'm just going to write down. And here's my t. I need to add 1 to this. So adding 1 is the same thing as adding 2 over 2. So this will be the 3/2 power. Then I need to divide by this new power. Dividing by 3/2 is the same thing as multiplying by 2/3. So I have this. Moving on to the next term, here's my minus 8. I'm going to take this t and I'm going to increase the power by 1. So I have t squared. But then I need to divide by my new power. So we can just do this in our heads actually. So 8 divided by 2 is 4. So let's just go ahead and put the 4. So we're going to have minus 4t squared. Time for the constant of integration. We can simplify this a little bit. 3 goes into 15 5 times, and then 5 times 2 is 10. So we will have 10t to the 3/2 power minus 4t squared plus c. This is pretty good, but we actually have enough information to figure out what c is. We're told that the particle is at rest at time t equals 0. So that means the velocity at time 0 is equal to 0. If the particle is at rest, that means that the velocity is equal to 0. So let's substitute 0 in for all of these t's and see what we get. So the velocity at time 0 should equal this expression that we get by substituting 0 for t. But we already know that v at 0 equals 0. So I'm going to go ahead and put 0 right here because we know that's the value of v of 0. And that should still equal this expression on the right. Since we are plugging in 0, this term is going to be 0, and this term is also going to be 0. So the only thing left is c. So 0 is equal to c. So I can go ahead and substitute 0 in to my equation, and then that will be the real answer. So this is my equation for the velocity as a function of time. For number 13, we need to find an equation for the particle's position y at time t. T is greater than or equal to 0. Well, we know that position, well, I started to put p, but it's on the y-axis. So the position function will be y at t. The position will be the integral of the velocity function. So substituting in what we have here, then y at t will equal the integral of 10t to the 3/2 power minus 4t squared dt. We can calculate this integral term by term using the power rule of integration. So, and there's my 10. I'm going to have t to the, I'm adding 1, so I'm adding 2 over 2. So this will be 5/2. So I have t to the 5/2 power. Now I will divide by 5/2, and that's the same thing as multiplying by 2/5. Moving on to the next term. There's my 4, and here's my t. Adding 1, I get t to the 3rd power. Then I divide by my new exponent, so that'll be times 1/3. And don't forget the constant of integration. We can simplify this a bit. 5 goes into 10 2 times. 2 times 2 is 4. So I have 4t to the 5/2 power. Not much I can do with this. I'm just going to put 4 over 3 t cubed plus c. However, we have enough information to figure out what c actually is. In the setup of the problem, we were told that at time t equals 0, the particle has position y equals 4. In other words, the position, well, let me not use p, I'm going to use y. The position at time 0 is equal to 4. Keep that in mind. So the position at time 0 is equal to 4. However, this is my position function right here. So if I want to calculate the position at time 0, I'm just going to put 0 in for these t's. We could do that in our heads, but I'm just going to show this for the AP graders so they can see my genius at work. And this is all equal to 4. But of course, these terms will equal 4 because, these terms will equal 0 because of these zeros. So I just end up with c is equal to 4. So we can substitute that in, and that will be the real equation. Kabam! Number 14, other than t equals 0, find all other times when the particle is at rest. Justify your answer. When you see the phrase, the particle is at rest, you should be thinking, oh, the velocity is equal to 0. So that's our strategy. Let's take our velocity function, set it equal to 0, and solve. Here's the velocity equation that we found in problem number 13. So let's take this and set it equal to 0. In order to solve this equation, we're going to need to factor. Let's factor out the greatest common factor. So I'm looking at the 10 and the 4. They're both divisible by 2. So I'm definitely going to take out a 2. But the variables are both t. I'm going to use the lowest exponent I see. 1.5 is less than 2. So I'm going to pull out t to the 3/2 power outside of parentheses. So now let's think about what will be left on the inside. I am dividing each of these terms by 2t to the 3/2 power. 10 divided by 2 is 5, so we have that. T to the 3/2 power divided by t to the 3/2 power is 1. So those cancel out completely. Moving on. 4 divided by 2 is 2. What about t squared divided by t to the 3/2 power? When you divide variables, you subtract exponents. So I need to do 2 minus 3/2. So I'm doing 2 minus 3/2. This is going to be 1/2. Maybe I'll do this off to the side. So we have 2 minus 3/2. 2 is the same thing as 4/2. 4/2 minus 3/2 is 1/2. So I end up with 2t to the 1/2 power. Now that I have this factored, I can solve by setting each factor equal to 0. So if I set 2t to the 3/2 power equal to 0, I'm going to get a solution. And if I set 5 minus 2t to the 1/2 power equal to 0, I'm going to get another solution. Well, this first one is just going to end up giving me t is equal to 0. And that's the one that we already knew from the beginning. So we're supposed to be finding values of t other than t equals 0. So, just ignore that one. I mean, it's true, it's a valid solution, but we already knew it. So moving on. Now we just need to solve this factor. Let's add 2t to the 1/2 power to both sides of the equation. I may need this space. Okay, so now I have 5 equals 2t to the 1/2 power. I just added this to both sides. Dividing both sides by 2, I'm going to have 5/2 equals t to the 1/2 power. Now I just need to get t by itself. How will I do that? Well, let's square both sides of the equation. On the left, that's going to give me 25/4. When you raise a power to a power, you multiply. So 1/2 times 2 is 1. So these numbers cancel each other out, and I'm just left with t is equal to 25/4. And this is the answer. This is the only other time other than 0 where the particle is at rest. Whoops, I almost forgot to justify my answer. Here you go. The particle is at rest at t equals 25/4 because the velocity at 25/4 is equal to 0. Number 15, find the general solution of this differential equation. A differential equation is just an equation that has a derivative in it. So don't be intimidated by these big words. If I want to find the solution, it just means to get rid of the derivative and turn this back into the original function. So if I take the integral, it should turn the derivative, which we see, back into the original function. So I'm just going to take the derivative I'm just going to take the integral term by term, and that'll be the general solution. So power rule. Raising this power by 1, I will have x to the third power. Then if I divide 6 by my new power, 6 divided by 3 is 2. So that should be the first term of my solution. I'm just going to go ahead and put this 4 down because I'm not using the power rule. For the cosine, I'm asking myself, the derivative of what is equal to cosine? I know that the derivative of sine is cosine. So that means the integral is sine x. What about this last term? I've got this minus sign here. We'll see if that lasts. This time I'm asking myself the derivative of what is equal to sine. Well, I know that the derivative of cosine is negative sine. That's super close. That means that the derivative of negative cosine will equal sine. So I need negative cosine for my derivative. But if I put a negative cosine right here, minus a negative is a positive. So let's go ahead and make this a plus. So plus cosine x. And this is going to be the general solution, so we can just go ahead and put c for the constant of integration. And that's it. This is the answer. Let me change one small thing. Because we started off with an equation, our answer should also be an equation. So let me include the f of x equals in the front of this. Number 16. Find the particular solution that goes through the point 0, 6. Basically, we are just using the point 0, 6 in order to find c. So 0 is going to be our x value, and the 6 is going to be the value of the function at x, right? In other words, the 0 is going to go in for all the x's, and the 6 is going to go way over here in the front. So I have 6 equals 2 times 0 to the third power plus 4 sine 0 plus cosine 0 plus c. I'm just trying to find c. This 0 term is going to become 0. I also know that the sine of 0 is 0. Do you need a refresher on this? I don't think you do. Sine is a y value. So 0 radians is right here. The y value is 0. That's why sine of 0 is 0. What about the cosine of 0? Well, cosine is the x value. And this is the point 1, 0. So cosine of 0 is 1. So let me just rewrite at this point. So I have 6 equals, maybe I'll just show my work here. So I have 0 plus 0 plus 1 plus c. All right, I'm just showing the breadcrumbs of knowledge. So this is going to quickly become 6 is equal to 1 plus c. Subtracting 1 from both sides, and we have 5 is equal to c. Now that we know that the c value is 5, we can substitute that back in right here. So I'm just going to recopy this whole equation, but I'm going to put a 5 in. Kabam! Last one, number 17. Show that capital F of x equals negative natural log cosine x is an antiderivative of lowercase f of x equals tangent x. An antiderivative is what you get when you take the integral of something. So we are basically supposed to show that this first function is the integral of this second function. But we have learned that the way you check your answer for an integral is take the derivative of the integral and you should get the original function back again. In other words, if capital F of x is an antiderivative of f of x, then the derivative of capital F of x should equal f of x. So basically, this is what we need to show. So we need to take the derivative of capital F of x. In other words, we're taking the derivative of negative natural log cosine x, and we're just going to see what happens. Hopefully, when all the dust clears, we will be looking at tangent x. Long ago, we learned that the derivative of natural log x is 1 over x. So I see that negative sign there. I'm just going to go ahead and put that down. So I'm moving on to the derivative of natural log something. So that's going to be 1 over something. In this case, 1 over cosine x. Because this is a function and not just x, I need to do the chain rule and multiply by the derivative of cosine. The derivative of cosine is negative sine x, which I will put in the numerator. Actually, notice that we have a negative times a negative though, so I'm going to move the sine x to the numerator, but I'm also going to take away these negative signs because they cancel each other out and make a positive. But suddenly we are finished because sine over cosine is tangent. So there it is. We showed that the derivative of capital F of x is equal to lowercase f of x.